Hello, everyone. My name is Radoslav Vuchkov, and I'm a fourth year graduate student from UC Merced, and this is my video for SIAM Annual 2020. So let's go into our slides. So today we'll be talking about Quasi-Newton methods for infinite dimensional inverse problems governed by PDEs. This is a joint work with my mentor, Professor Noemi Petra from UC Merced, and Dr. Kalman Petra from Lawrence Livermore National Laboratories. And this work was funded by NSF and the DOE. First, I'll give you a motivation why we developed these Quasi-Newton methods for infinite dimensions. Then I'll walk you a little bit through the proofs, and then give you numerical evidence of the effectiveness of these formulas. So first of all, my group, we solve inverse problems, and inverse problems can be formulated as constraint optimization, where you have objective function and a constraint. In our case, the constraint is a PDE, or partial differential equation. This can be physically interpreted as having a membrane that's being pushed by a force F, and U represents the location on the membrane where we are, and M represents the stiffness of the membrane, and this is the parameter we're trying to invert or solve for. And we're trying to do that using some sparse data, UD, that's given on the membrane. So typical methods for solving optimization problems such as this is steepest descent, which is the most robust method, but also not really effective on this kind of problems because it takes thousands and thousands of iteration. It's slow to converge. Then there is Newton method, which has superior convergence properties. And if we can use it, we would, but the problem is the Hessian is often not available, or even the Hessian apply. So that leaves us with the methods we'll be talking about today, which is Quasi-Newton methods, where we build a Hessian approximate using only gradient information. So Quasi-Newton methods generally take more iterations than Newton methods, but each iteration is cheaper because it uses only gradient information. So you might end up having as a total cost the Quasi-Newton methods being cheaper than the Newton methods. So the most common used finite dimensional Quasi-Newton methods are DFP, Davidon-Fletcher-Powell, which was the first Quasi-Newton method found in 1960 by Davidon in Argonne National Lab. And then there's Broyden-Fletcher, Godaf-Susano, the BFGS, which is considered the king of Quasi-Newton methods. BK here stands for the Hessian approximate of iteration K, and HK stands for the Hessian inverse approximation at HK, because in some methods it makes more sense to approximate the Hessian inverse directly. SK is the difference between two iterates, and YK is the difference of the gradients of those iterates. So there is an existing literature of Quasi-Newton methods in infinite dimensions, but often the formulas are more of an analogy of the finite dimensions, so they're not really derived or proven. The only paper we have found that provides a proof of a Quasi-Newton method, it was BFGS, and it was done by Professor Eckhard Sachs from Trier University. So that left space for our contribution, where we managed to derive through different methods, Quasi-Newton methods in infinite dimensions, and we proved a variety of them, including BFGS, DFP, SR1, and PSB. The primary challenges for us were finding the proper setting where this theory makes sense, right? What kind of operators do we want to work with? What kind of spaces do we want to work with? So this is one of our formulas. This is the formula for DFP, and this looks like a watt. So what I really want you to focus on here is that what we really do is we formulate this variational problem, this minimization problem, where we're asking to find a B such that it minimizes this norm, right? And B is constrained. This is called the secant constraint, and W satisfies some constraint. The solution to this is the DFP update. So, and the rest of the theorem just tells you that this behaves as expected as in the finite dimensional, given some conditions. So I'll give you an idea of our proofs in general, how we arrived at these theorems. So we actually solved this much simpler quadratic problem with the secant constraint by using two tools. One is the Hilbert projection theorem, which is a necessary condition. You can think of the infinite dimensional version of a KKT conditions, and the geometric lemma, which also corresponds to a part of the KKT conditions. This geometric lemma really is an extension of a theorem done by Guler in 2009, where they did for finite dimension, and we extended that for our infinite dimensional theory. After that, through some U substitutions, you can easily shift this problem to this. And then, depending on what constraints we put on the W operator, we'll get a different update formula. So we claim that for this much simpler problem, which we'll refer to as the problem in blue from now on, the solution is of such. And this space, B00 is a space of Hilbert-Schmidt operators that made the most sense for us. They're also known as trace class operators. So just for notation, before I talk about the geometric lemma, BS is the space of symmetric operators or self-adjoint. A is the space of all operators that satisfy the secant constraint. And L is of large interest to us, is in particularly when y is 0. Si is like a change of basis that we introduce to for simplicity. In terms of this operator is outer product. So in finite dimension, this will be nothing more than S transpose EI. So this term will do nothing more than recover the Si entry of the vector S. So this allows us to inspect things pointwise in a sense. So this is our geometric lemma. So what you should think of is, for example, in finite dimensions, you have the KKT conditions where they tell you that the Lagrange multipliers need to live in the orthogonal complement of a certain space. So this is what this does. It describes that orthogonal subspace. So L, the first part, this is nothing more than reformulation of the L given here, where it allows us to look at the SIs instead of the general S. This in optimization is referred to as the central cone. And part 3 is really the important thing here. It tells us that the Lagrange multipliers will have a very specific shape. The shape will be like this. So here S will be fixed and lambda is the unknown. So if you can figure out what lambda is, you have figured out your Lagrange multiplier. Okay, so going back to the proof of the problem in blue. So if you have a quadratic, what you do is you take a first derivative and a second derivative. If the second derivative is positive, then you have a minimizer, and this is the identity operator, or 1, which is always positive, so this will be a minimizer. So then if this was finite dimensions, we'll say by the KKT conditions, this has to live in the L perp space. For us though, because we're in infinite dimensions, this is called the Hilbert projection theorem, and it tells us the solution has to live in this perp space, in this orthogonal complement. But luckily for us, we completely understand this complement for our geometric lemma. And we know that it has to look like this. So this is one equation when the unknown is lambda. But we also have from the problem in blue a constraint. So we have one equation and one constraint. So we should be able to solve for that, or one unknown and one constraint. And through just some algebraic manipulation from here, you can see that you can solve for lambda. So from there, I'm not going to give you what U substitution we used, but you can transform that problem in blue into this, and this looks much larger and scarier. But the benefit now is that we have this W operator that allows us a freedom, right? And depending on what we require from W, we can get a different update. So for example, if we require from W to satisfy the secant constraint, we'll get the DFP update. And if we require W to satisfy the W inverse to satisfy the secant condition, then we'll get the BFGS update. And similar transformations or constraints can be required from W to get PSB and SR1, and also their inverses. Our framework also allowed us the freedom to develop limited memory versions in infinite dimensions. So that's great for constraint optimization. So now let's apply this in a numerical example. So that's the PDE for the membrane, or the inverse problem for the membrane. So here we are fixing some of these parameters. We're working on a square one by one, and we're using a Tikhonov regularization. So what we did also is we introduced the so-called structural updates, where this, because this is user chosen in a sense, we know the Hessian of this term. So the structure updates would use that. And that's just a different thing from the infinite dimensional, but the idea is that this problem has a very particular form, and we can really take advantage of that. So we want to now compare how infinite dimensional formulas would do to the comparison to the finite dimensional. So what you should be looking at is in red, that represents if you used out of the box your MATLAB BFGS or your NumPy BFGS without any preconditioner. And what we're doing is we're solving this in finite element, and we're making the mesh more and more fine, increasing the number of parameters. And the number of iterations increases. And here it's already in thousands. Versus if we use our infinite dimensional formulas, you see that the number of iterations remains relatively the same. So that's called mesh independence. It's highly desirable property for large scale optimization. And you see this phenomenon happening also for BFGS and DFP. And then our third methods where we're using these structural updates also retains this property, which is great. So in conclusion, we developed Quasi-Newton formulas in infinite dimensions. We illustrated their effectiveness in how they have demonstrated mesh independence. And we have our paper accepted by the Journal of Numerical Optimization and Functional Analysis of Journal of Numerical Functional Analysis and Optimization, and details can be found here. Thank you very much, and goodbye.